Next, case 2, where the two population standard deviations are assumed to be equal. Our parameter of interest is still mu sub 1 minus mu sub 2, the difference between the two population means. In the previous example, we looked at a case when the variances are unequal. Now we have the case where the two variances or standard deviations are equal. So again, the same. And in this case, we want to look at the hypothesis testing and confidence interval. So parameter of interest is still mu sub 1 minus mu sub 2. And the point estimate is still x bar sub 1 minus x bar sub 2 from the two samples we take from the two populations. Now this time, we can compute what is called a pooled variance estimate. When the two standard deviations or when the two variances are equal, then we can pool the two sample variances as a weighted average of the degrees of freedom. And what we get is a pooled variance estimate S squared sub p. Now, using S squared sub p, then we can compute the standard error of x bar sub 1 minus x bar sub 2 with this formula. So this is a more accurate estimate of the standard error if the two standard deviations are equal. So that's why if they are equal, or two variances or standard deviations, if they are equal, we need to use this formula for standard error, not the one that we used previously. Now, for us to apply the formulas, we need to make sure that the sample sizes are large enough so that approximating normal distribution will be valid. Then the confidence interval formula is the difference in the point estimates plus or minus the pooled estimate of the standard deviation times 1 over n sub 1 plus 1 over n sub 2 in square root. And the degrees of freedom now is a lot easier to compute n sub 1 plus n sub 2 minus 2. Now hypothesis testing, the same three types as before. Now the test statistic is going to be same as before, except that the standard error is now different in the denominator. And once you compute the test statistic, we can use the t dot dist functions for the p-value. And the degrees of freedom is very easy, n sub 1 plus n sub 2 minus 2. But we are going to use the Excel data analysis command to get this whole thing done. Now let's look at a special case. Okay, what if the two population standard deviations, which are still unknown, but they can be assumed as equal, which is not a bad assumption because we normally want to test or develop confidence interval for two similar concepts, like starting salary of HRM majors, starting salary of marketing majors. And the population standard deviations are likely to be the same. So if that is so, we can come up with more precise estimates of the population variance, and so our test will be more discriminating. So how do we do that? And when the two standard deviations are equal, then what we can do is we can do a pooled variance estimate and use the pooled variance estimate for our calculation of the t-value. And in that case, our standard deviation, our degrees of freedom will also be different. So we'll use the same data as before, same hypothesis test. We want to test whether average HRM starting salary, the alternative hypothesis is greater than the marketing majors. So let's get the sample size and sample standard deviation from up here. So that's the first sample size, and the sample standard deviation is here. Okay. So now if we copy these over to the next column, that will give us for the second sample. Okay. Now degrees of freedom here is given by n sub 1 plus n sub 2 minus 2. Okay, if you look at the textbook, I've already gone over the formulas for this in the previous video. So n sub 1 plus n sub 2 minus 2 gives us the degrees of freedom. Now for pooled variance, we need n sub j minus 1 that is sample size minus 1 times the variance. So let's do that for each sample. So it will be like you take the first n minus 1, that's the degrees of freedom for the first sample, times this, take the standard deviation and square it. Okay, so that's for the first sample, and then do the same for the second sample. Now the pooled variance estimate, okay, is you take the sum of these two and then divide by the degrees of freedom. Okay. So if you look at the formula, you'd see that that's what, so here is the formula. N, the first sample, okay, and the second sample, then divide by the degrees of freedom. So once you find the pooled variance estimate, then we can compute the standard error by taking the square root of the variance and then multiplying by this factor, which is what we're going to do now. Okay, so these are the computations for pooled variance estimate. Now standard error is you start with square root of the pooled variance, so convert that into a standard deviation, and then you multiply by square root of 1 over the first sample size plus 1 over the second sample size. Okay, we needed 2 right side brackets. So that's our standard error. So T calc then is T calc then is the point estimate. We did this for the previous example, minus D sub 0. Now this time we're going to divide by not this standard error, but the new one, which is a little bit smaller than before. That's the advantage of assuming that the two standard deviations are equal, if that assumption is a valid one. You can't just simply assume, there should be a reasonableness to it. Okay. So then we do the test first using the t-table approach. Now we have t.inv. This is a one-tail test, and we need to give the, this is a one-tail test, so we have to give the cumulative probability. It is 1 minus alpha. That, comma, the degrees of freedom this time is 103. So that's our t-table value. So conclusion is, since our t-calc is greater than t-table value, we reject the null hypothesis. It's exactly same as before, but slightly different t-value. Now p-value, again, we need to use t dot this dot rt, and the new t-calc, slightly different. The degrees of freedom is also slightly different, so p-value will be slightly different as well. Okay. So it's even a smaller probability of being wrong. So same conclusion as before, and so interpretation is going to be the same interpretation